Today is Chapter 10, Section 5. We're going to be talking about the multiplication of radicals. We've talked about the addition and subtraction in the last section. Alrighty, so in this section we will learn how to multiply radicals by using the multiplication property of radicals. So the property is, let A and B represent real numbers. Now here, that's a big thing here. Real numbers, okay? I say it's a big thing here because, ooh, there's some stuff on my screen. Because we're only going to be able to use this property if our numbers are not not imaginary. Okay, so we'll see later. I don't know if we touch on it in this class. I'm pretty sure we do, but I'll come back to this definition when we do start to talk about multiplying imaginary numbers, because this rule does not apply if we have imaginary numbers. But anyway, so we're going to represent real numbers such that the nth root of A and the nth root of B are real. Okay, then the nth root of A times B is the same thing as saying the nth root of A times the nth root of B. Okay, so similar to how we would split up factors of the radicand. Then this is essentially kind of the same process, except now we're moving into, well, we can multiply radicals. And the cool thing is they don't even have to be like radicals, and we'll see that at the end of the section. Okay. To multiply two radical expressions, we use the multiplication property of radicals along with the commutative and associative property of multiplication. So basically what this is saying is, all these nice words right here, what it's basically saying is that to multiply, you do it the way you think you do, right? That you've been taught, that you've learned how to do. So nothing really changes, except now we just have radicals. Oh my, that looks like a lot of work, doesn't it? Alrighty, so let's start with 1. We've got 3 on the square. Let's put up here. We'll do 3 on the square root of 2. Alright, so instead of actually rewriting it, what I'm going to do is I need to rewrite it. That way you see where things are coming from. Sometimes I forget that. Can't read my mind, right? Alright, so what we're going to do here is we're going to multiply the real component, or not the real, but the non-radical numbers, and then we're going to multiply the radicals like this, okay? So it's going to look something like, and I'll keep those underlined for right now. 3 times 5, well, that's 15. And then square root of 2 times square root of 6, well, that would be a square root of 12. Okay. All right, but we're not done. Square root of 12 can be reduced. Okay, what can we reduce to? It can be reduced to, is there a perfect square factor? Yeah, there's a 4 in there, right? So 4 times 3. And same procedure I've been doing so far, right? I always underline what I take out. So I can take out the square root of 4, so that ends up being 15 times 2 on the square root of 3, which would end up being 30 on the square root of 3. Okay, and that's how we do that. Again, we just multiply the numbers on the outside of the radical, and then we multiply numbers on the inside of the radical, and then the numbers on the inside of the radical, whenever we multiply them together, we're probably more than likely going to be having a perfect square factor inside. And again, in this particular case, it was at 4. And let's go ahead and just, instead of jamming everything into one, we'll just get a new page here. Okay. I don't know. I don't feel like I explained that fully. Maybe I did. All right. All right, let's do B, and we'll just go ahead and use all this since we're going to go ahead and put all these on a separate page. Okay, so let's go ahead and rewrite it. All right, and again, underlining the numbers on the outside here, and then I'm going to underline the numbers on the inside where my radical are located, rather. Okay, so we're gonna multiply the things I underlined in red, so it's gonna be 2x and a negative 7, so it's gonna be a negative 14x. Okay, then we're gonna multiply the numbers inside the radical. Although I guess they're not numbers, they're variables, right? So it's gonna be the square root of xy squared. And let's fix that x a little bit. Okay, well, we have a perfect square in there. Okay, the perfect square is y squared. So we know that that can be pulled out. What's the square root of y squared? Well, that's just y. So we're going to have negative 14xy on the square root of x. Okay, let's do one more just like that. Naturally, it gets just way more complicated looking, doesn't it? Okay, so C. I don't know if I wrote B on the previous one. Alright, so I did. Alright, so let's rewrite it. We've got a 15C on the cube root of CD times 1/3 cube root of CD squared. Okay, so again, we're going to multiply the outsides, and then we're going to multiply what's on the inside. Okay, well, what is 15 times 1/3? Well, that's 5. Right, a third of 15 is 5. And we have the C. And what's on the inside of the radical? It's a cube root, so remember that cube root there. Looks like it's going to be c squared d cubed. So c squared d cubed. We're going to underline that d cubed because that's what we're taking out. And honestly, it might just be better if yeah. I'm going to put it right here. I'm going to go back and change b to be the same way. Well, what's the cube root of d cubed? That's just d. So we're going to have 5cd on the cube root of c squared. Okay, and of course c squared, again, c squared is not a perfect cube, so it's going to stay in there. Right? And let me go back and clean this up. I like to put the equal signs underneath each other if I can. So. Okay. All right, and that is how we do those. All right. Now, of course, that was the easy one. We have plenty of examples today, so today's not going to be a 14-minute lecture. All right, that is just if we just straight up multiply them against one another, right? Like 7 times 4. Next, we're going to have to use the distributive property. Right? But the thing is, all of these properties, they behave the way that you think they do. Okay, so everything that we have seen and done before, we're going to do it here. So let's write 3 on the square root of 11 times 2 plus the square root of 11. That's going to be interesting. Okay, so what I meant by that is, if this was just, and I think you can actually just go ahead and see it without me changing the variables here. But we distribute through there and distribute through there, and then we just clean it up. Okay, we just use the distributive property. Okay, so we've got 3 on the square root of 11 times 2, so it looks like it's going to be 6 on the square root of 11. And it's going to be plus, okay, well, this is interesting. So it's going to be plus 3, it's going to be plus 3 on the square root of 11 times the square root of 11. Okay, so let's go ahead and just examine what that's going to look like before I actually write it in my solution there. Okay, well, we multiply the numbers on the outside. Well, that's easy. It's going to be 3. Okay, and then we got the square root of 11 times the square root of 11. Well, the square root of 11 times the square root of 11 is going to be the square root of 11 squared. And of course, what we know that to be simply 11, right? So it's going to be 33. So this is going to be plus 33. Right? And that's it. Well, example 2 is way shorter. Ooh, oh man, oh yeah, I know what's in store today. It sucks. It's just gonna be we're just gonna be distributing a lot from here on out. I feel like. I wonder if I can fit both of these on the same page. Probably not, but we'll see. All right, so let's start with A. Um, yeah, yeah, we won't try to force one page. We'll just put these on separate ones. So let's go ahead and rewrite it. So we've got the square root of 5 plus 3 on the square root of 2, 2 on the square root of 5, minus the square root of 2. Okay, so again, we're just going to distribute. In this particular case, we know that this distribution property has a name, right? It's called FOIL, first, outer, inner, last. Now, the FOIL is just distribution when you have two binomials, right? Because you have the first, then you have the two outers, then you have the two inners, then you have the last ones, okay? But, I mean, all FOIL is just, again, distribution. So let's begin. We're going to start with the square root of 5 times 2 on the square root of 5. So again, it's the square root of 5 times square root of 5. Well, the square root of 5 and the square root of 5 is the square root of 5 squared, which is just 5. And actually, instead of saying that, let's just go ahead and let's write this out one last time. Actually, we'll just do square root of 5. Okay, if we have the square root of 5 times the square root of 5, okay, we know that to be the square root of 5 squared, which we know to be 5. Okay, and again, we're going to see that quite often. I'm supposed not only for the 2's here, not only for the square root of 2's there, but I'm pretty sure we'll see it again the rest of the lecture. Okay, so we're going to have 2 on, again, the square root of 5 times square root of 5 is 5, so it's going to be 2 times 5. Let's actually put that in parentheses. Okay. And then we're going to do the square root of 5 times the negative square root of 2, so it's going to be minus the square root of 10. And then plus, it looks like 6 on the square root of 10. It's a big old flag there, isn't it? 10. Then we're going to have minus 3 times just 2, because again, it's going to be 3 on the square root of 2 times the square root of 2. Okay. Well, now if we clean that up, we're going to have 10. And it looks like we can combine those like terms. So we're going to have a negative. This is what we did the other day here. Again, I'm looking here. You know, it's essentially a negative 1 on the square root of 10 plus 6 on the square root of 10. So we have like radicals, so we can just combine those. So to be a plus 5 on the square root of 10, and then minus 6. Well, then we can do even more combining here. Actually, let's just put it underneath it. You know, 10 minus 6, so that's 4. So 4 plus 5 on the square root of 10. And the square root of 10, its factors are 2 and 1, 1, 2, and 5, and so we can't break that down anymore. So that would be the solution. Alrighty, so let's rewrite this again. Oh gosh, see, that's oh no, it's still 2. We will get to 3 terms though. It looked like 3 for a moment. I guess I got tired eyes here. Alrighty. Let's begin the distribution process. So we're going to have negative 10, looks like a squared, and it's going to be, again, the square root of b times the square root of b, so it's going to just be a b. And it's going to be plus, no, it's going to be minus 20 ab on the square root of b, and we're going to have plus 7 ab on the square root of b, and then plus 14b squared. Okay. Alrighty, So the first term here, it doesn't have any like terms to go with it. So we got 10a squared b. I'm going to look here at the middle terms, right? So they have the same variables, good, and they have the same like radicals. That's also good. So we can just simply say, you know, negative 20 plus 7. So we're going to have negative 13 ab on the square root of b, and then plus 14b squared. Right. That wasn't so bad. Whew. All right. So with that said, a lot of what this section is going to be doing is just absolutely positively mindless computation. Okay. Again, it's computation that you're familiar with. It's computation that you've seen before. It's just you got to go at it, right? There is a lot of room for error whenever you have to do this mindless computation. Okay. So make sure that you take your time. And I mean, maybe for the first couple, do it twice. I don't know. But take your time with these because they do get very tedious very quickly. And you see that with this problem. This looks like it's about to be very tedious very quickly because it's not, you know, again, FOIL is just with two binomials. But this is a binomial, right? A term, or a fact, well, multiplying two terms. And this has, is that, no, it is. Yeah, this has three terms. I mean, I was about to say, is that two terms too? Here we have the 6 with the negative x, negative square root of x, and then 8 on the square root of y. So what I'm going to do here is I'm just going to multiply. I'm just going to multiply through pretty much the whole thing. I mean, I am going to multiply the whole thing. It's just gets very tedious. Actually, I'm going to keep those arrows there, mainly because they look really nice. Okay, so you think I should rewrite this? I think the arrows will do their job. Yeah. So we're going to have 12 on the square root of x. And then we're going to have minus 2. Okay. And it's going to be minus 2 on the square root of x times square root of x. Wait, so it's going to be minus 2 on the square root of x squared. Okay. Well, again, the square root of x squared is just x. So I can write x there. And then we're going to have plus 8 or plus 16 on the square root of xy. All right, that takes care of the first bit. Okay, all the top arrows essentially. Then we're going to move on to the bottom arrows. So we're going to have plus 6 on the square root of y. Okay, and then we're going to have minus the square root of xy. Then we're going to have plus, again, here we go. We have 8 on the square root of y squared. So it's just going to be plus 8y. All right, we're going to combine like terms here. Do we have? Oh yeah, it looks like we have one like term. Okay, so it looks like, you know, this 12 on the square root of x, it stays all by its lonesome. Which one? Minus 2x, that stays by its lonesome. All right, but we do have like terms here: 16 on the square root of xy, and then a minus, you know, again an implied 1 on the square root of xy. So we can say that that is plus 15 on the square root of xy, and then plus 6 on the square root of y, and then plus 8y. Whew. Looks good to me. Alright, well, that's how we do that. Again, I guess the big thing is just the arrows, right? We need to know how to distribute there. My arrows look better. Alright, this example should take like 14 seconds. Alright, so I guess maybe it's just like a nice refresher of what we've seen before. Although I do feel like maybe this should be what we started out with, because we've done a lot of the you know, same number squared to basically get rid of the radical and the square, right? Let's snip this along with it. All right, so this reads up here, the multiplication property of radicals can be used to simplify an expression of the form the square root of a quantity squared, where a is greater than or equal to 0. And of course, again, like I said, I feel like this is something that we probably should have covered first before because we've done this a lot already, haven't we? We're on example 5, and I'm pretty sure we've done this on the first 4 examples. If not the first 4, maybe 3 of the first 4. The logic can be applied to the nth root. Of course, we know that. We've done these examples. Well, let's get started. Okay. So a, the square root of 11 quantity squared. All right. Well, again, we know that that is just simply 11, right? B, the fifth root of z to the fifth. Well, that's just z. And C, we've got the cube root of pq quantity cubed. That's just pq. Okay. Now, real quickly, you might remember something about absolute value. Remember doing that whenever we had our ends be even, right? Well, we didn't put an absolute value on 11 because, well, what is the absolute value of 11? Well, it's just simply 11. Okay. That's about it for that. Ain't much more to say, is there? Alrighty, so special case properties. Think we went over these special case properties before. So again, nothing new. I'm looking right here. Okay. It says, recall that the square of a binomial results in a perfect square trinomial. We've done this before. I told you need to memorize these formulas. A plus b quantity squared. Ooh, this is actually a good point. So, okay. Now, I know it's very tempting. It's very, very, very tempting to, if we see an a plus b and then, square both of them. It's very tempting to write that, okay? But this symbol right here means does not equal to. I say that because many students want to do this when they see this. Don't do that. We do know that a plus b quantity squared does equal to this, a squared plus 2ab plus b squared. Okay, and of course that makes sense because we know that when we see the exponent, the 2 there, this, we know that that's essentially saying this twice. So we'd write it twice. Okay, which is where we get the a squared plus 2ab plus b squared. Now, using this it's our power rule. Okay, it would work if it were a times b quantity squared. Then it would be a squared b squared. Okay, but if we have that addition or that subtraction sign right here, never do this. Bad. Okay. But anyways, those are the formulas. These formulas need to be memorized if you don't have them memorized already. It's not something that you're going to just use in this course. You're going to use it, honestly, up until differential equations or something. If you make it that far, if you want to go that far, rather, mainly because these kind of problems are just really easy to play with and easy to manipulate, and the more we can use our brain and recall things, the better our mind works, right? So this isn't just a memorize this for example 6 or this section or this class. Memorize it for the next class and the next class and the next class, right? All right, so let's begin. A, we can just simply, we don't have to rewrite it, right? Because we know the formula. It is this is an addition sign in there, right? That's an addition sign. So all I have to do is follow this one. Okay, so this is in the form of a plus b quantity squared. So it's a squared. What's the square root of d? What's the square root? I'm sorry. What is the square of the square root of d? Square. Oh shoot! You know what I'm trying to say, right? So, no. Let's back it up. Come on, Sherman. You get paid to do this. What is the square root of d squared? There it is. So the square root of d squared is simply d, right? And then it is plus 2 times a times b, okay? Well, if this is the a and this is the b, essentially, right? What is 2 times that? Well, 2 times 3 is 6, and 6 times the square root of d is 6 times the square root of d, so that's what that is. So we're going to say plus 6 times the square root of d, and then plus b squared. Okay, so again, this is the b. Well, 3 squared is 9. And there is no like terms to deal with, so we can move on. Man, my computer just got really dusty all of a sudden. I wonder if it's the fan. Okay, so b, right, this is going to be the subtraction one because this is a minus sign there, this is a minus sign here. Okay, so it is in the form of a minus b quantity squared. So we're going to say, okay, so a squared, so it's going to be 5, it's going to be this, times that, right? So 5 on the square root of y times 5 on the square root of y. Well, that's going to be 25. All right, and again, what is the square root of y squared? Well, that's just y. And it's going to be plus 2ab. So again, 2 times 5 on the square root of y is 10 on the square root of y. And then 10 on the square root of y times the square root of 2 is 10 on the square root of 2y. Right, that went terrible. So 10 on the square root of 2y. And then lastly, it's going to be, that should be a minus sign there. And then lastly, we do b squared. So what is the square root of 2 squared? Well, that's just going to be 2. Okay. Now, real quickly, if for any reason, and I say for any reason, but maybe just starting out, you don't feel like using those formulas, okay? Now, I implore you to use these formulas. They're easier. Actually, they are easier. They're easier and they're quicker, okay? But if you want to slow things down and actually see what things look like, you are more than welcome, if you need to do this. Oops, not squared. You're more welcome to do this, and then do the FOIL process. Okay. If you took this, what I just did, and you FOILed it, you would get my solution for A. Okay. But again, it's a lot more writing and it's a lot more time consuming. I do want you to memorize our formulas, but if you're not there yet, if you don't feel comfortable yet, you want to take things slow, go ahead and write out those 2 binomials and FOIL. But this is so much better. You'll be proud of yourself. Okay, so we're going to talk about the difference of squares now. So basically, again, like I said from the onset of this class, that everything that we have done and everything that we're used to, we're using those exact same rules, and we see that come into play here, right? Especially, talking about difference of squares. Well, if we look at the difference of squares, okay, we know that that equal sign says that we can essentially we can go one way or go the other way, right? So these particular problems are written in a manner where we're not actually expanding. Okay, if I say expanding, we'd be going from here, from this form to this form. Instead, we're going to try and condense it. Okay, so what we're going to do, well, let's first talk about conjugates. We have seen conjugates and heard of conjugates before. A conjugate basically is where these terms and these terms are the exact same, but the only difference is the sign. Okay, that's what makes a conjugate. And we can see in this example that we do indeed have 2 conjugates, right? For A, the first term, they're both the square root of 3. The second term, they're both 2. The only thing separating them is that sign. Okay, so let's actually take A and break it down, and then we'll do B quickly. Okay, so what is the a term in a? Okay, well that's the square root of 3. And what is the b term? That is 2. Okay. Now I say a term and b term because I'm gonna follow this formula perfectly. Okay. So if I were to say a is the square root of 3 and b is 2, then sure enough I would have a plus b and then a minus b. Okay. Hopefully you're following along there. Again, just looking here at this problem. All right. So again, if a is the square root of 3 and b is 2, then I have this set up as a plus b, a minus b. And let's actually change the color there. I'm going to keep that there. So I'm going to keep a plus b and a minus b. Okay. Well, then I just need to make it equal to a squared minus b squared. Ooh, I got an idea. Okay, so I'm gonna actually write the problem beneath it. That way we can see that one-to-one example there. Okay, just like that. All right. Well, what is a squared? What is the square root of 3 squared? Well, that's just going to be 3. And what is 2 squared? So 3 minus 4. Right. And then 3 minus 4 is indeed equal to negative 1. Okay. I think that's good. Isn't that a genius idea there? to write that formula underneath it. All right. So let's move to B. So for B, I'll set this up the same way I did A. So what is my A value? Oh, okay, so this is nice and ridiculous. 1/3 on the square root of S. What is my B? That is 3/4 on the square root of T. Okay, so same thing as before. We're going to go ahead and write A plus B. Let's actually make it a little bit bigger because I think those fractions might present a little bit of a problem size-wise. Okay, so here we go. Just the A term again is 1/3 square root of S minus 3/4. I don't like that minus sign hanging up there like that. Square root of T. So it's still in the form. Actually, let's be more precise here because the minus sign does go first. Okay, so I did something there. I said because I did have a plus here and a minus here, right? And then I said, well, you know, let's actually stay consistent and actually line these up. Okay. Again, the thing is, it doesn't necessarily matter, right? It doesn't matter because 4 times negative 3 is negative 12. 3 times negative 4 is also negative 12. So it does not necessarily matter. But I feel like to keep things nice and simple and easy on the eyeballs, I wanted to go back and make things nice and pretty, right? Okay, so my A is 1/3 on the square root of S. So we got to square that. So we're going to say 1/9. And what is the square root of S squared? That is simply S. Okay, and then it's going to be a minus B squared. So it's going to be, again, we're looking here. It's going to be 3/4 quantity squared. So 3/4 quantity squared is 9/16. Right, 9/16, and that's going to be times T. Again, because what is the square root of T quantity squared? Well, that's just T. Okay, well that takes care of that. Last example. Alrighty, so now this is a big one. I said earlier we can multiply. So unlike addition and subtraction, when we add and subtract radicals, the radicand, okay, again the number inside my radical, and my index, right, the number in the little the number in the little cubby hole right here, right, they must be the same when you add or subtract. When you multiply, you can do whatever you want to, right? And so let's explain that. So a is the fifth root, or I'm sorry, the cube root of 5 times the fourth root of 5. Okay, well, how do we go about that? What does that mean anything to you? Okay, well, let's first of all remember that we can rewrite this as 5 to the 1/3 times 5 to the 1/4. Okay, so now we're going to recall what we did before when we had when we multiplied when we multiplied exponents, we must have like bases, right? Okay, well, we have like bases, so we know this will turn into so let's actually change my exponents here. We're going to get a common denominator. Okay, that common denominator looks like it would be 12, right? So let's write it with a denominator of 12. So that's going to be 5 to the 4/12 times 5 to the 3/12. Okay, so put a little. Let's fix that 4 there. There we go. All right, so 5 to the 4/12 times 5 to the 3/12. All right. So what we're going to do now is combine them back, right? We have two exponents with like bases. So if we are multiplying that, then we just basically add the exponents together, right? So it'd be 5 to the 4/12 plus 3/12. Okay, so that's going to be 5 to 7/12. Okay, and then we know we can rewrite 5 to 7/12 as the 12th root of 5 to the 7th. Okay, so real quick, I'm gonna recap that. So we have 5 to the 1/3 times 5 to the 1/4. Okay, and we are wanting to we're wanting to write the answer in radical form. Well, we can't just write cube root of 5 and the fourth root of 5 because we can't use the rule we used earlier because we don't have like radicals. Instead, what we have to do is we have to rewrite our exponents. Okay, and again, our exponents would be 1/3 and 1/4, right? That is what the cube root and fourth root looks like if we broke it down into fractional exponents. Okay, and then once we did that, what I did here was I found a common denominator from my exponents, right? Again, 4/12, that is 1/3. 3/12, that is 1/4. Okay, and then I combined those, and I know that if I take exponents with like bases, and again we have a like base, they're both 5, then I can just simply add them together. 4 plus 3 over 12, which is 7/12. And then I have this, and then I know I can rewrite that in radical form because the denominator becomes the root, and then the numerator becomes what we multiply on the inside. I mean, we could have put the 7 on the outside. Okay, again, if you recall, they're the exact same, right? So doesn't matter either way. So let's do B. Now B looks like a doozy. All right, so let's go ahead and rewrite these in my my fractional exponent form. So B, we're going to write 7 to the 1/3, and that's going to be times 2 to the 1/2. Okay, so we're going to use the same kind of idea that we did on the previous page. 7 to the 1/3, 2 to the 1/2. Okay, so a common denominator, that is a pretty easy one, right? It's 6. So we're going to write 7 to the 2/6 times 2 to the 3/6. Okay. Well, now we can't combine these two because they don't have like bases, right? We have a 7 and a 2. But instead what we can do is look at the denominator of my radical there, and I can say, oh, well, this isn't terrible, right? That it's going to be the sixth root of 7 squared and 2 cubed. Okay, so it's going to be the sixth root of 7 squared times 2 cubed. Okay, and again, the squared just happens to be here, and this cube is here. Okay, and the 6 here, well, this is the 6 right there. Okay, but we can actually take this a little bit further, can't we? So, we'll put an equal sign down here. The sixth root of, well, we know what 7 squared is. That's 49. Times 2 cubed, we know that's 8. Okay, and then 6 on the the sixth root of. Okay, so 50 times 8 is 400. 49 times 8 would be 392. Okay, and the sixth root of 392. And I'm just going to stop there. Yeah, because I don't know if there is a perfect sixth root inside 392, and so I'm not even going to try. And luckily, it looks like there is not. Okay, alrighty. That does conclude today's lecture.